For page 58, label it holes and vertical asymptotes. And then we're actually going to come down to the bottom. You can go ahead and paste your paper in here. Leave yourself some room at the bottom. Looks like about 7 or 8 lines from the bottom so that you can make a few notes. But that's actually where we're going to start. We'll come back and talk about this table and what's going on and what we're talking about with the vertical asymptote versus the hole in just a second. But let's look at the example first. So the example that we're working with, you'll notice that's in both of these tables. We've got through x squared minus 12x minus 15 divided by x squared minus 3x minus 10. And so that's what we're going to write down here, and we're going to see what's going on in this example. So we're going to learn that in rational functions, there are possible times that you could have either a vertical asymptote or a hole. And so we want to be able to locate these things because our goal is to be able to graph a rational expression or a rational function. In order to graph it, we need to see some of its key features. A vertical asymptote and a hole is one of these key features that we want to be able to graph. So this is the example that we've begun with. This is the same example from the table above that I showed you. And so the first thing we want to do is we want to factor that. So there is a GCF of 3, so we'll go ahead and pull that out. And then once we pull that out, we'll be able to factor the top, and the numerator will look like this, 3 parentheses x plus 1, x minus 5. At the bottom, you could factor that into x plus 2 and x minus 5. So what you're going to notice is that these two guys up here, x minus 5 and x minus 5, are the same thing. So you can actually cancel those out. And you're left with 3 parentheses x plus 1 over x plus 2. So mathematically, we see that something got canceled out. One of the bottoms that made the bottom 0 would be x equals 5, and one was x equals negative 2. So these would be part of your domain restrictions for the original function. X cannot be equal to negative 2, and x cannot be equal to 5. But what happens when you cancel out this x minus 5? And what happens with this x plus 2 that remains here at the bottom and x equals negative 2? Does that mean x equals 5 is no longer a problem on our graph since it gets canceled out and there's no more 5 at the bottom of a fraction? So let's see what happens there. So it says to find a vertical asymptote or a hole, you've got these 4 steps here. So number 1 is to factor and cancel, which is exactly what I did. Number 2 says factor that you have left gives you your vertical asymptote. So down here, the factor that we have left is x plus 2. And it's saying that I can find my vertical asymptote from that. Notice I've boxed it up here and here to show you what it was talking about. Number 3 says the factor that you canceled gives you your hole. So we canceled out, and I highlighted these 2 factors that got canceled out. That gave us our hole. And then it says plug in x of hole back into simplified form to get y value. So you would plug in your factor that got canceled out, that whatever made that 0, which is 5 in this case. You would plug it in back here to see what the y value is. So let's see how that compares to our actual graph now. This is the actual graph of this f of x that we've got. And so if you notice here at x equals negative 2, there really is a vertical asymptote there on the graph, and that really was the last thing left. X plus 2, if you set that equal to 0, is x equals negative 2. So that actually matches that there is a vertical asymptote here because it is the factor that got left, like number 2 stated. Now, if you come over here, you'll notice that there's a hole. It's at x equals 5. We'll come up with the value of y in just a second. So at x equals 5, it says that we're going to have a hole according to number 3. Factor that got canceled gives us our hole. And so that would have been x equals 5, and that does match. There's a hole right there. But it also says that in order to figure out the y value, you plug it back into your simplified form. Well, I did that over here. I say hole is at x equals 5. Here is my simplified form. I plugged in 5 into my x. So that gives me 6 times 3 at the top divided by 7. So 18 divided by 7, if you put that in your calculator, is 2.57. If you look here, this is somewhere between 2 and 3. There really is a hole, and it's going to be at 5, approximately 2.57. And so that actually matches our work as well. Okay? So these are the steps for finding vertical asymptotes and holes on a graph. So now let's see what happens in a table. If we were to look at a table instead at our graph and see what's going on, how we can locate it that way. Because I will give you a table without a graph and ask you to find the hole or the vertical asymptote. So let's see what's happening at these domain restrictions. Remember, we had domain restrictions from the very beginning. We said x cannot be equal to 5 and x cannot be equal to negative 2. So if you notice here in my values, I've got negative 2 in my table, and I've got 5. And you'll notice I plugged in very, very close points to negative 2 on the left and the right, and then the same thing for 5. And I want to see what's happening to my y values as we see that. So we said on page 57 that we're going to have a vertical asymptote if y goes up forever or down forever, increases or decreases without bound, as x gets closer to a number either from the left or the right. Well, if I look at the left-hand side of -2, let's see what's happening to my y values as I do that. So, for example, if I plug in -2.1, I get 33 from this y value here. If I plug in -2.01, I'm going to get 303. If I plug in -2.001, I'm going to get 3003. But if I plug in -2 itself, remember that made that bottom 0, so it's going to be undefined. So when I'm plugging in -2 itself, that makes the bottom 0, so therefore I can't really see what's happening there, so it's going to be undefined. But if I look strictly at the left-hand side, as these numbers, -2.1, -2.01, -2.001, get closer and closer to -2 on the left, notice these y values are getting very, very high significantly. Y is actually getting closer and closer to infinity. And that would be true if I plugged in, for example, -2.0001. So the way that I write that is that as x approaches -2, I have a little superscript here from the left, y approaches infinity. And this is how I would know that there's a vertical asymptote at x equals -2 by looking at a table. Now it only has to happen on one side, but we'll go ahead and look at the other side and see what's happening. So now if I plug in numbers to the right of -2, for example, -1.9, -1.99, -1.999, and these numbers are getting closer and closer to -2, but now from the right-hand side, you'll notice that the y values are actually going down, but they're going down very quickly. They're jumping significantly, which means the way that I would write that is x approaches -2. I have a superscript from the right this time. Y approaches -infinity. And this just also further just shows that we have a vertical asymptote at -2. Now, let's see what's happening in our table at around x equals 5 instead. So I'm going to plug in numbers to the left, 4.9, 4.99, 4.999. I'm going to plug in numbers to the right, 5.1, 5.01, 5.001. Now, if you look at these y values, all of them seem to be hovering around about 2.5. They're not jumping up significantly on the left and right like these did with my vertical asymptotes. They actually look like they're getting closer and closer to a number. We've got a 2.56 here, 2.570, 2.571, same thing on the right-hand side. So actually this does not fit that definition of having a vertical asymptote because these y values are not increasing or decreasing without bound on the left side and right side of 5. So something different must be happening. And in this case, this is what was happening. This is, remember, x equals 5 was the value of the factor. The factor was x minus 5, x minus 5 at the top and the bottom. That was the factor that canceled. And so as a result of it being gone, it actually created a hole in the graph. It's like it created a hole in the equation, which in turn created a hole in the graph itself as well. And so now that's where this value is coming from, this 2.57. Notice those are the same values that I'm hovering around. So the way that I write that this time is as x approaches 5 from the left, y approaches 2.57. That means I'm looking on the left-hand side of 5. I'm getting closer and closer to it. And my y values are getting closer and closer to 2.57. On the opposite side, as x approaches 5 from the right, my y values are actually approaching that same number, 2.57. So I would consider this a hole at x equals 5 based on what the table is showing me. So the differences between the tables is that in a vertical asymptote, the y values will jump significantly either to infinity or -infinity. And in a hole, they'll actually get closer and closer and try to hover around a specific number. And that's going to be the difference between the table. You already can see what's the difference in the graph, the hole versus the vertical asymptote. And in an equation, the difference is that the hole is where the factors got canceled out, and the vertical asymptote is the factor that got left. Whatever makes that 0 is where your vertical asymptote is going to be. And that's it for this page.